Welcome to G Fun Facts Online, the place where we unravel the amazing world around us. Today, we're diving deep, literally, into how humanity figured out the size and shape of our own planet Earth long before we had satellites whizzing overhead. It sounds like a colossal task, right? And believe me, it was. So picture this: ancient Greece. Scholars there weren't just philosophizing about life. They were looking up at the sky and down at the ground, trying to make sense of it all. One name that shines brightly from this era is Eratosthenes of Cyrene. We're talking about the 3rd century BCE. This brilliant mind came up with a way to estimate Earth's circumference with astonishing accuracy. How did he do it? Well, he noticed that on the summer solstice, the sun was directly overhead in a city called Syene, no shadows. But in Alexandria, further north, a vertical stick cast a shadow. Eratosthenes measured that shadow angle, knew the distance between the two cities, and with some clever geometry, boom, he calculated the Earth's circumference. Depending on the exact length of the stadion unit he used, his estimate was incredibly close to what we know today. Others like Plato and Archimedes also gave it a shot. And later, Posidonius used observations of the star Canopus. These early thinkers, along with Thales of Miletus developing geometry and Claudius Ptolemy with his geocentric world system, laid some serious groundwork. Fast forward a few centuries, and we see a major upgrade in measurement techniques. Enter triangulation, which really took off in the 16th and 17th centuries. Imagine you have 3 points forming a triangle. If you know the length of one side, that's your baseline, and you measure the angles at each point, you can use trigonometry to calculate the lengths of the other 2 sides. Then, you just create a chain of these interlocking triangles, and suddenly you can measure vast distances and map huge areas. A Dutch astronomer and mathematician, Willebrord Snell, systematically used this method back in 1615 to measure the distance between Alkmaar and Breda. These triangulation networks became the backbone for national surveys, mapping out large chunks of Europe, the United States, and even India by the late 19th century. The first really notable geodetic survey using triangulation was in France, started by Jean Picard in the late 17th century and continued by the Cassini family. Alongside triangulation, surveyors also used trilateration. This is where, instead of angles, you directly measure the lengths of all 3 sides of the triangle. This became much easier in the 20th century with the advent of electronic distance measurement, or EDM, instruments. And then there was traverse surveying. Think of it like dead reckoning for land. You measure angles and distances between a series of connected points to figure out their positions. But what about the Earth's actual shape? Was it a perfect sphere? The genius Isaac Newton, in the 17th century, theorized that because the Earth rotates, it should actually be an oblate spheroid, a bit squashed at the poles and bulging at the equator. To prove this, the French Academy of Sciences funded 2 incredible expeditions in the 18th century. One team, including scientists like Pierre Bouguer and Charles-Marie de la Condamine, went to Peru, near the equator. Another, led by Pierre-Louis Maupertuis, ventured to Lapland near the North Pole. By meticulously measuring the length of a degree of latitude in these very different locations, they confirmed Newton was right. The Earth indeed bulges at the equator. This was super important for creating more accurate mathematical models of the Earth, called reference ellipsoids. Of course, there were other crucial techniques and tools. Astronomical observations were key. By measuring the angles between the plumb line, which shows the direction of gravity, and stars, surveyors could determine latitude and longitude, establishing vital control points for their maps. Then there's leveling, used to measure height differences between points. This helped in understanding things like land subsidence or uplift. Precise leveling networks were developed, even accounting for tricky stuff like atmospheric refraction. And let's not forget gravity measurements. As early as 1902 in Canada, scientists were making precise gravity measurements using cool devices like the Mendenhall pendulum apparatus. Understanding these tiny variations in Earth's gravity helped them define the geoid, essentially the true shape of the Earth if it were all covered by sea level. None of this would have been possible without some nifty instruments. Theodolites were absolute workhorses, used for accurately measuring horizontal and vertical angles in triangulation and traverse surveys. These evolved from having micrometer circles to advanced optical instruments like the Wild T4, getting more precise all the time. And I mentioned electronic distance measurement, or EDM, earlier. The invention of instruments like the geodimeter in the mid-20th century, which used light waves to measure distances, was a game changer. It drastically cut down the time and effort needed for baseline measurements in triangulation and made trilateration much more practical. It wasn't just individual efforts either. There were significant international collaborations. One standout example is the Struve geodetic arc. This was a massive chain of triangulation survey points stretching all the way from Norway to the Black Sea, measured between 1816 and 1855. It was a monumental project aimed at determining the Earth's size and shape with even greater accuracy. So all these pre-satellite techniques, while incredibly laborious and time-consuming compared to what we can do today, were absolutely essential. They laid the foundation for our understanding of Earth's size, shape, and gravity field. They enabled the creation of accurate maps, helped with navigation, and provided the crucial data that later satellite-based systems were built upon. When Sputnik 1 launched in 1957, it heralded a new era. Systems like GPS, satellite laser ranging, and very long baseline interferometry have given us unprecedented precision and global coverage. But it's truly awe-inspiring to look back at the ingenuity and sheer perseverance it took to measure our world, using just observations, math, and some very clever instruments. That's all the time we have for today on G Fun Facts Online. Thanks for tuning in, and I hope you join us next time for more fascinating insights into our world. Stay curious.